Dear friends, welcome back. In our previous lecture, we discussed about a wing and tail combination and the stability of that wing and tail combination. We derived neutral point for wing and tail combination, which figured out to be the weighted average of lifting characteristics of wing and the tail, right? So we started with the wing whose aerodynamic center is located at XAC with respect to the leading edge of the wing. Say this is my location of the aerodynamic center, AC of wing, which is XAC of wing. So this wing and tail are positioned with respect to fuselage reference line. This is our fuselage reference line. And this aircraft is flying at a velocity v infinity, and the aircraft angle of attack is considered as wing angle of attack, and we assume the wing aerodynamic center coincides with this fuselage reference line. And then we have a tail combination. Say this is my tail, which is symmetric. Why? Because I need to produce equal amount of force when deflected either upwards or downwards. So for that case, I want to have a symmetric tail here, so which is inclined at an angle I of t with respect to fuselage reference line. And then due to the downwash of the wing, and first of all let's figure out the aerodynamic center of the tail, AC of tail, right, which is located at a distance XAC of tail. So XAC of tail with respect to leading edge of the root chord. And now the CG of this combination is assumed to lie somewhere in between wing and tail, and the corresponding location is XCG of this combination. Now due to the downwash of the wing, we know because of the presence of the wing there is a downwash near the tail, right? That's because of the wing. So due to which the resultant angle of the resultant flow will be V infinity prime, which is different compared to that of V infinity here, right? So what the aircraft is facing. So the initial or the wing V infinity is parallel to this, right? These two, let's assume these two are parallel, and then there is a modified flow at the tail due to the downwash, which is the effect of epsilon, right? Now the total angle of attack of tail, alpha t, in terms of known quantities, like what I know here is alpha I know, so this is alpha ideally, this is alpha, and what I know is alpha subtracted by epsilon will give me the V infinity or the flow at the tail with respect to the fuselage reference line, right? So alpha minus epsilon is this particular quantity, added with this inclination of the tail will get me the total angle of attack at the tail, right? Alpha at tail is equals to plus I of t. And we also witnessed that epsilon can be modeled as a function of CL naught and CL alpha, isn't it, right? So this is like 2 times of alpha I, and this can be expressed as epsilon naught plus dou epsilon upon dou alpha times alpha, isn't it? So this epsilon is a function of angle of attack at the wing, right? Downwash at the tail varies due to the variation in the angle of attack at the wing. So this is not alpha t, this is alpha, so you need to remember that. And then if you write the total lift equation from here, say now the lift at the tail will be acting perpendicular to V infinity prime, and we neglected the effect of say horizontal component. Why? Because there is no offset here. So, and effectively we assumed a small angle of attack, and hence the lift of the wing directly contributes for the positive pitching moment, and the lift of the tail contributes towards negative pitching moment about the CG here that we are considering, right? So all these distances are measured with respect to leading edge of the root chord of the wing, and which are parallel to this fuselage reference line. And again for wing we are not commenting whether it's a cambered aerofoil or a symmetric aerofoil or a reflex aerofoil. That means we need to consider the moment about aerodynamic center of the wing, right? So with this we can proceed to figure out what is the total lift generated by this aircraft. The total lift of this aircraft with the principle of superposition, which is one of the assumptions that we considered earlier, is the combination of or the summation of the lift generated by the wing and the lift generated by the tail, which is L of the total aircraft is L of wing plus L of tail, and then we figured out that CL of total aircraft, or which is equal to CL naught of total aircraft plus CL alpha times alpha of the total aircraft, which is equals to CL naught of wing plus eta St upon S times CL alpha of tail times I of t minus epsilon, right, minus epsilon naught here. So this plus, so CL alpha of wing plus eta St upon S CL alpha of tail 1 minus dou epsilon upon dou alpha times alpha. Right. So with this, by comparing the coefficients and constants of alpha, what we have is the total zero lift coefficient of the aircraft of the UAV is equals to, is contributed from zero lift coefficient from the of the wing, and there is a correction factor to the tail setting. See, due to the tail setting, zero lift of wing is 0, of horizontal tail is 0, because zero lift at zero angle of attack there is no lift coefficient, it's a symmetric aerofoil. So the contribution is because of the initial tail setting, which is constant throughout the flight. That means such a amount of, like, the lift coefficient times CL alpha times the angle of attack, which is nothing but the, at zero angle of attack, V infinity prime is aligned along with this flow, isn't it? Let us assume there is no epsilon. V infinity is aligned with the fuselage reference line. Effectively, there is no angle of attack. Since we have given a tail setting, which is I of t, the aircraft will continuously experience some lift because of the tail, right? Even at zero angle of attack. Though this is 0, but still there is a constant CL alpha times I of t. No, in a loose sense, like this will be the contribution of tail lift towards the pitching moment, right? So, and throughout the flight it will be constant, and increases will become a summation as there is a change in angle of attack, or when you are changed to a different angle of attack, there will be an additional component because of that particular angle of attack at the tail. So CL naught of the wing times, place, so the modified lift coefficient CL alpha of tail times I of t minus epsilon naught. Okay. So this is the CL naught of the aircraft, and CL alpha of the aircraft is CL naught, CL alpha from the wing, the contribution comes from CL alpha of wing straight away, and this modification, so eta is a modification, eta of horizontal tail is nothing but half rho v square, v prime square upon half rho v square, that can be 1, right, when there is no downwash, that means epsilon can be 0. So if you have equal wings, like same wings as wing and tail, that means what you have is just CL alpha times I of t. If I of t is also 0, let us say, then what you will be having is CL naught, CL naught of wing plus CL naught of tail directly. Okay, here similarly, similar contribution comes from CL alpha of tail 1 minus dou epsilon upon. So this is the total aircraft CL naught, or the UAV CL naught and UAV CL alpha. Similarly, we have pitching moment about CG. So is moment about CG or O, or the, so okay, moment about CG or the moment about entire object or this UAV is equals to the positive or the pitching moment, positive pitching moment provided because of lift generated by the wing. Apart from that, the wing also have moment about aerodynamic center. It has a component. The wing has a component which is moment about aerodynamic center about the wing, and then there is a positive contribution of lift from the wing and times the xCG minus xAC of wing, which is the momentum, minus eta, or say lift of tail times, there is no, since it's a symmetric airfoil, moment about aerodynamic center of the tail is 0, and this lift from the tail contributes towards negative moment, that's why minus t, and the moment is due to the force at the tail, which is L of t, times the momentum between CG and AC of tail. That is nothing but xAC of tail, right, or xCG removed from xAC of tail. Right? This is xAC of tail, If I remove xCg, this is what I end up with. So what I have is x AC of tail minus xCg. That is a corresponding momentum. By doing this, the Cm naught of the total aircraft is given by Cm AC of the wing plus CL alpha of the CL naught of the wing times xCg bar minus xAC bar, which is x bar upon c bar minus eta st upon s times CL alpha of tail times 1 minus x AC of tail bar minus x bar CG times I of t plus epsilon naught. Okay. So you can express this way, right? Isn't it? 1 minus dou epsilon by dou alpha times alpha plus I of t minus epsilon naught. So this particular term contributes towards negative moment. So I am taking minus common out. So what I have is this. Okay. And Cm alpha of the total UAV is CL alpha of wing times x bar CG minus x bar AC of wing minus eta st upon s, which in general this product st upon s times x bar AC minus x bar CG is known as tail volume ratio, where x bar AC minus x bar CG is called LT bar, length of the tail in non-dimensional character, in non-dimensional form, or L of t, which is xAC of t minus xCg in dimensional form. CL alpha of tail times x bar AC of tail minus x bar CG times 1 minus dou epsilon by dou alpha. Okay. Yeah, please correct this. This should be minus epsilon naught. So it has to be. So it contributes towards positive. When I of t is negative, this contributes towards positive value here. Right. So this is CL naught is the same thing, right? It is from the CL naught itself. I of t minus epsilon naught, but it is giving pitch down moment, that is minus of that, right? So okay. So this is the total Cm naught and Cm alpha for longitudinal. In order to talk about longitudinal static stability for this UAV, we need to consider these two parameters, Cm naught and Cm alpha, and Cm naught has to be greater than 0 and Cm alpha has to be less than 0 in order to have longitudinal static stability. And further we proceeded to figure out what is the neutral point of this configuration, which is x and p. It's a location of the CG, right, for which of the entire aircraft, for which this Cm alpha becomes 0, or the pitching moment is independent of angle of attack. The variation in pitching moment is independent of angle of. That means about neutral point we have Cm naught, but not Cm alpha. Right? Cm alpha will be 0. So by substituting that Cm alpha 0 to 0 and then replacing this xCg to the corresponding x and p, what we can find out is x bar np, which we have derived in our previous lecture, is equals to x bar AC of wing times CL alpha of wing. So these are very important. You need to practice this so that you will be able to remember them, or say without derivation you will be able to figure it out. If you practice multiple times and if you keep digesting the facts what we have derived here, you will be able to write down what I am trying to do right now. Right. So again here it's a modified CL alpha, it's a correction factor to the CL alpha of tail, which is eta st upon s times CL alpha of tail times 1 minus dou epsilon by dou alpha. So all this is the correction factor to the CL alpha here, which we have discussed earlier. And then CL alpha of tail, x bar AC of tail upon, otherwise you can do it this way, CL alpha of wing times, so let's write CL alpha ahead of that, x bar AC of wing there it is x bar AC of tail upon the total CL alpha of this aircraft. What is the total CL alpha of this aircraft? It's CL alpha, right? CL alpha of the wing plus eta ST upon S is a correction factor to the CL alpha of tail times 1 minus dou epsilon by dou alpha. Okay, this is a neutral point. And now we also talked about static margin, which is the difference between the neutral point x bar NP minus x bar CG, right? So from here we have derived that the static margin is equals to, if I substitute this x bar NP here and then minus x bar CG, what I end up with is minus of Cm alpha upon CL alpha of the entire aircraft, which is equals to minus dCm upon dCl. So that means if you have positive static margin, right, you have negative slope. Like so when for a statically stable aircraft, the Cm alpha, when you have positive static margin, you will have negative slope, right? Cm alpha will be negative for an aircraft which is statically stable. Okay, so I think with this we will now proceed to solve few example problems. Let's dedicate maybe this entire week to solve these problems. Why? Because this is what is going to help you for the design. Now we talked about wing and their contribution towards stability, and tail and its contribution towards stability. And then what is design? We need to know what should be the area, what should be the offset, no? What should be the location, what should be the area of the tail, what should be the area of the wing, and what should be the location of wing and tail, what should be CL alpha of wing and tail, right? Isn't it? So we talked about all the major parameters that governs the design of wing and tail. For us to understand or digest these things better, we need to solve few example problems, right? So while solving these example problems, we will consider a straightforward solution where we assume we know CL alpha of wing and tail and their locations, and we will try to figure out what are its stability characteristics. Or we will also try to find out what will be the neutral point and all. These are the straightforward problems. Once we get used to it, when we are approaching or solving that iterative method, we will try to approach it in a reverse way, where we will try to have these parameters and try to figure out what should be the wing location, what should be the CL alpha of the wing or CL alpha of the tail airfoil, right? So we will try to get those parameters, design parameters, for you to select a particular airfoil in order to build such a wing and tail combination. Okay, so let's proceed to solve few examples. So I am going to erase all these equations which you must be having already. So once you practice these derivations, you will be able to enjoy. Otherwise it becomes difficult. You may think that these equations are too lengthy, no, to remember, but still if you practice, that is nothing. From the first principle, if you start deriving them by yourself a couple of times at least, so you will be able to appreciate what are all the terms and why there is a correction factor to the tail. So all those terms you get comfortable with, and then you can start using for your design process with more confidence. So let's take up the first example. So the aerodynamic center of a wing of UAV is located at 0.2 MAC and CG, or center of gravity, is at 0.25 MAC. Using the following data, determine horizontal tail area to give a minimum static margin of 0.08. Amazing. Okay. So the data given is CL alpha of wing is given as 0.1 per degree, CL alpha of tail is given as 0.08 per degree, and zero lift angle of attack alpha CL is equals to 0 as -1 degree, and it has a 0 tail setting angle. I of t is given as 0, okay, 0 tail setting angle, and CMAC of wing is -0.01, okay, and epsilon is given as 0.45 alpha, okay, and then LT bar is given as 2.5 with a tail efficiency factor of 0.95. Okay, so and the area of the wing, so the area of this wing is about 25 meters square. So please expect these questions, the similar questions in your examination. Right? So you need to get used to this particular data and all these coefficients that we are using here. So that can happen again only with practice. So what we need to do here, we need to find out the horizontal tail area when the static margin is given. Right? So here we have static margin, we got to know what is the location of aerodynamic center of the wing as well as center of gravity location. So what does it mean? Let us say this is my fuselage difference line. Let's say this is my leading edge of the wing, and what I have is x or aerodynamic center of the wing, which is XAC located at, which is equals to 0.2 C bar, okay, 0.2 C bar. So that means like they have non-dimensionalized this distance, right? That means x bar AC is 0.2, okay. So given solution, XAC of wing is 0.2 C bar, which is again how much? 0.2 times C bar is given, right? Isn't it? C bar is not given? Yeah, C bar is not given. So let's keep it as it is. So this implies x bar AC of wing is 0.2. Okay, and x bar CG, say this is my CG, location of CG. XCG is 0.25 C bar. So x and XCG is given. XCG is 0.25 C bar, which means this implies x bar CG is 0.25. Okay, and then the length of the tail is also given. Let us say this is my AC of tail, and it is located at a distance XAC of tail, XAC of tail, but this is not given straightforward. We got a LT bar. What is LT bar? Which we just discussed. So LT bar is equals to LT bar is equals to LT upon C bar, which is equals to X AC time X. It's a distance between, we call it as tail arm, right? So it's a distance between aerodynamic center of the wing of the tail and the center of gravity of the aircraft. Right? X bar AC minus of tail minus X bar CG upon C bar. This is equals to X bar AC of tail minus X bar CG. Fine. So this value is given as 2.5. This is equals to 2.5. So now X bar AC of tail from here, X bar AC of tail is 2.5 plus X bar CG. So this is equals to 2.75. 2.75 in the non-dimensional form. So what you have is 2.75 C bar. This particular distance is 2.75 C bar. Okay. We are now with that given data of LT, we are now able to figure out what is the location of aerodynamic center of the tail. Okay. And then tail efficiency factor is given, eta is given 0.95. So epsilon it is given. So what is epsilon is equal, epsilon naught is 0. Since from this data we just have dou epsilon by dou alpha. There is no epsilon here. So epsilon naught is equals to 0. And so I'll try to highlight what we have derived till here. So we have this particular factor and we also have this and also epsilon naught, right, and dou epsilon by dou alpha is equals to 0.45. This is another thing, another parameter, variation of downwash with angle of attack at the wing, right. So CL alpha of wing is given, let's convert it into radians, right. CL alpha of wing is equals to 0.1 per degree, which is equals to 5.73 per radian, right. Yeah, this is 5.73 per radian. We have another value, and then we can also talk about CL alpha of tail, which is how much? CL alpha of tail is given as 0.08, CL alpha of tail 0.08 per degree. So this is equals to CL alpha of tail is 4.58 per radian. Okay. So this is my, this is one of the parameter that I require to solve this problem. So this is what I can see. Alpha at which CL0 is -1 and I of t is 0. CMAC of the wing is also given. So this is what I have, and again static margin is given here, right. So static margin SM is equals to, static margin is equals to X bar NP minus X bar CG, which is 0.08, right. See, it is already in C bar, in MAC, right. So if we just take X bar NP minus XNP minus XCG, then it is 0.08 C bar. No. So it's already, we are talking in terms of non-dimensional numbers. So let it be 0.08 then. So if you substitute the CG location here, you will be able to find out what is the neutral point, isn't it? So can we do that? This implies, so otherwise this implies X bar NP neutral point is equals to, so 0.08 plus X bar CG. So 0.25 plus 0.08, which is 0.33. So I now got the location of neutral point. Now I need to figure out, with this data I need to figure out what is the tail area. We also have the tail setting angle, data about tail setting. From the neutral definition of neutral point, X bar NP. So can we find out something? So I immediately can see what is X bar NP from the definition of neutral point, right. So I will try to figure out whether I will be having adequate data to find out what is ST. in order to have this particular static margin, right? So this is equals to x bar CL alpha of wing times x bar AC of wing plus, see I am intentionally writing these equations again and again so that you will get used to it. Okay. So I wish you should also take down the notes for this. Eta St upon S times CL alpha of tail times 1 minus dou epsilon by dou alpha multiplied by x AC of tail, x bar AC of tail upon CL alpha wing and the correction factor to the lift curve slope of the wing due to the downwash and the area of the wing. Right. So you are normalizing the area of the wing here, 1 minus dou epsilon by dou alpha. So let us look at the parameters that we got. So we have CL alpha of the wing, right, isn't it? So which is highlighted here, and we have XAC of the wing. XAC of the wing is given, and we know what is eta. Eta of the tail is given as 0.95. So we have the data eta, and we don't know what is St upon S. This is what we need to find out. S is given 25 meters square, but we don't know what is St, which is need to be figured out from the data. So CL alpha of tail is given, so we just now converted it to per radian. So CL alpha of tail is available, and I have dou epsilon upon dou alpha, right, which is 0.45. So even I have this, and also we just figured out what is XAC of tail. Am I correct? So we just got what is XAC of tail. So XAC of tail is here, which is 2.75 in non-dimensional form. So that means we got all the data, and neutral point we have figured out from the given static margin. We have estimated what is the neutral point, right, with the given CG location. With the given static margin and CG location, we got where should be the neutral point. For me to have neutral point at this particular location, what should be the area of the tail? So that is what we can solve it from this particular equation. So you can simply substitute this, or say St upon S. If I rearrange this equation, what I can have is CL alpha of wing times x bar AC of wing minus x bar NP upon eta CL alpha of tail 1 minus dou epsilon by dou alpha. Okay. This is in the denominator. I am taking this common out. So multiplied by x bar NP minus x bar AC of tail. Am I correct? Yeah. Aerodynamic center of wing is ahead of the neutral point. So that is what we will be ahead, because you know 0.33 is the neutral point and 0.25 is the aerodynamic center. 0.2 is the aerodynamic center. So this will be a negative term. So negative upon negative, because neutral point lies in between aerodynamic center of tail and aerodynamic center of wing. That means it is lesser than the XAC of tail. So this is a negative quantity again. So negative upon negative, what you have, the ratio is positive here, St upon. So if you can substitute these values here, so CL alpha of wing is 5.73 per radian multiplied by XAC of wing minus x neutral point is about, so this is like 0.25 plus, so 0.33 minus 0.2, which is 0.13. Okay, so this equals to minus 0.13 upon, so eta is 0.95 from the given data, and CL alpha of tail is 4.58. We converted into per radian multiplied by this correction factor due to induced downwash from the wing, right? So this is 1 minus 0.45, which is 0.55 I guess, multiplied by the distance between neutral point and the aerodynamic center of tail, which is again 2.75, 0.33 is like 0.42, right? Minus 2.42. Minus 2.42. Yeah. So can you quickly solve this? So what I have is St upon S is equals to 0.1295, which means St is close to 13% of S, right? So the tail area is 13% of that of wing area, just 13% of wing area. So the wing area you have is 25 meters square. So what it will be? This implies St is equals to 0.1295 multiplied by 25, which is 3.24 meters square. Okay, that's a wing area we need to figure out. So from the given data we are able to find it out. Yeah, sorry, that's a tail area. I'm sorry. So given the wing area, we are able to figure out what is the tail area. What should be the percentage of tail area in order to have this static margin. So what will be the tail volume ratio? Can we find the tail volume ratio of this? So the tail volume ratio VH, V of horizontal tail, is St upon S times LT upon C bar. This is nothing but St upon S times what is LT? X bar, XAC of tail minus XCG upon C bar. This can be written as VHT is St upon S times X bar AC of T minus X bar CG. This is equals to, so 0.1295, that is approximately 0.13 multiplied by times XAC of tail minus XCG bar. So this is this value. What is that? So 2.75 minus 0.25, right? So this is a corresponding value. What is the value here? 0.323. Now also find the Cm alpha of this aircraft. Find, so let us say this is part A, example 1A, one part A, and solving part B. For the above UAV, find Cm naught, find Cm alpha and Cl alpha of the UAV. From the above data, find Cm alpha and Cl alpha of the UAV, right? So we know from the static margin, definition of static margin, what we have is minus Cm alpha upon Cl alpha of the entire UAV. This implies, if I want to know what is Cm alpha, this is minus static margin times Cl alpha of the UAV. So how can I find Cl alpha of the UAV? So Cl alpha of the entire aircraft is Cl alpha of wing plus eta St upon S times Cl alpha of tail multiplied by 1 minus dou epsilon upon dou alpha. Can we find this? So it is 5.7, 3 plus 0.067 or say 0.95 multiplied by 1.1295 multiplied by 4.58 multiplied by 0.55, okay, times 0.5. So Cl alpha of the entire aircraft is 5.73 plus 0.31. So see, the major contribution of CL lift curve slope for the entire aircraft is from the wing here compared to that of tail, isn't it? Am I correct? So that's because, so the major, what do you call, so eta is close to 0.95, that is not going to affect the CL alpha much. It's just almost 95% of CL alpha, and the downwash, see, it's almost made half of that CL alpha, and from that the tail volume ratio is just 13%, so in that half it is making 13% of that half. That's why the contribution is very, very less here, isn't it? So this is equals to 6.04, yeah, 6.04 per radian. Okay. Once you have CL alpha, it is easy to find out static margin. Sorry, we have static margin and CL alpha, so we'll be able to find out CM alpha of this UAV with the current CG location. Right. So with the current CG location, CM alpha is equals to minus of static margin times CL alpha of the entire UAV. So this is minus of 0.08, right, static margin multiplied by 6.04. Location CM alpha, this implies CM alpha is equals to minus of 0.48 per radian. Okay. So we are able to find out the CL alpha, both. The CL alpha is 6 per radian approximately, and then the CM alpha of this UAV is minus 4.48, minus 0.48. So can we comment about stability right now? Can we comment about longitudinal static stability? I don't think so, isn't it? So we just know what is CM alpha. We need to find out what is CM naught of the aircraft as well. So let's consider part C of this question. Part C is, so comment about the static stability of the UAV, right, and the corresponding trim angle of attack. We need to find that, right? So for this, we'll have this data alpha at which CL is equals to 0 is minus 1 degree, and I of t is equals to 0, and CM AC of the wing is minus 0.01, right? So these are important. So to comment about static stability, we need to find out CM naught here, right? The CM naught of this wing and tail combination is given by CM AC of wing. You have to refer to this equation again, right? CM AC of wing plus CL naught of the wing times the momentum x bar CG minus x bar AC of wing, right? Minus of, we have a negative contribution, right, or a negative moment due to tail, and the setting is what is going to make it positive for CM naught. So ST upon S times CL alpha of tail, right? This completes half rho v square S CL alpha of tail, completes the lift at the tail, isn't it? In non-dimensional lift curve slope at the tail times the corresponding downwash effect, right? So times the setting angle, not the downwash effect here. So what is the setting angle? I of t minus epsilon naught times x bar AC of tail minus x bar CG. Am I correct? So CM naught is equals to, what is CM AC of the wing? Minus 0.01 0.01 times CL naught of the wing. So do we have the information about CL naught of the wing? No, right? What we have is CL alpha of the wing and alpha at which CL is equals to 0. What does it mean? So if you look at this, if you look at the variation of CL with alpha, right, of the wing here, we are talking about wing. So let us say it's a cambered aerofoil, so that's visible from CM naught, CMAC of the wing. Right? Because it's negative, I can say it's a positively cambered aerofoil. So what I have is a linear regime, CL alpha, I know this CL alpha, dCl upon d alpha, I know this, and I need to find out this CL naught given alpha at which CL is equals to 0 is minus 1 degree. So I know these coordinates which are minus 1 degree comma 0, and I know these coordinates 0 comma CL naught. So by using the definition of slope, I can find out CL naught of wing is equals to minus of CL alpha of wing times alpha at which CL is equals to 0. Okay. So this is approximately 0.1. Right. So this is 0.1. Okay. So now, yeah, substitute this 0.1 here, and we know I of t is 0, epsilon naught is 0. Here, from the given data, I of t is 0 and epsilon naught is 0. This term vanishes. So what you have is CL naught of the wing here, and then the difference between XCG and XAC. So CM naught will turn out to be CMAC minus 0.01 plus 0.1 times the distance between CG and the aerodynamic center of wing, which is 0.05, right? So what this turns out to be 0.005, right? 5 times 10 power minus 3. Yeah. Positive but very small, isn't it? 0.005. So positive but very small, very small number. So what we can say is CM alpha is negative and CM naught is positive. We can say this is statically stable. It possesses longitudinal static stability, this particular UA, with the current CG location. So how can I increase this? So before, are we satisfied with the CM naught? How can I answer that question? So we have another part, which is the corresponding trim angle of attack, right? So do you remember this plot, the CM variation with alpha? So CM variation with alpha, so CM naught has to be positive and CM alpha has to be negative, which makes this aircraft to trim at a particular angle of attack called alpha trim. So this corresponds to trim, isn't it? Alpha trim. Am I correct? So this value is CM at alpha 0, which is CM naught. So you have CM naught and you have CM alpha, dCm upon d alpha. So can we find out alpha trim? By definition from the definition of this slope, right? CM alpha is equals to CM naught minus 0 upon 0 minus of alpha trim, right? Am I correct? So this implies alpha trim is equals to minus CM naught upon CM alpha. So this equals to minus of 5 raised to the power of 5 multiplied 10 power minus 3 upon CM alpha is minus 0.48. Minus 0.48. So from here you can figure out alpha trim, which is equals to 0.5 degrees approximately. Right? Alpha is equals to, alpha trim is equals to 0.6 degrees or 0.01 radian. So this is approximately 0.5, right? Can't you consider this as 0.5? So this is like 10 power minus 2 upon, yeah. So this is equals to 0.6 degrees approximately, right? So that means this trim at, so this particular angle is 0.6 degrees, no, not even 1 degree trim angle. You're not able to trim the aircraft, no. So from the design, it is trimming only at 0.6 degrees, not even at 1 degree. And we know from the CL versus alpha, at 0.6 degrees, the value of CL is quite less. We may not be flying at the desired CL. The design CL, we call the corresponding CL for this particular trim angle of attack is the design CL, may not be satisfied with this particular alpha trim. So we have a horizontal tail, but we made the tail setting angle 0. So what must be the reason? We haven't taken the contribution of the tail. We made it I of t 0. Okay. So we haven't included the contribution of tail. Though we have a tail, but it is not contributing towards this trim. Right. So yes, as we discussed earlier, there will be an additional drag due to the trim or due to that setting called trim drag. Right. So but still we can't afford such a low angle trim angles for this aircraft. No? So that means if you have to trim at a higher angle of attack, you need to give elevated deflection, which again increases the drag a lot. So which is not desirable. So what should we do right now? What as a designer do you think about this? Okay, to have a better feel, let's now have a tail setting angle. Let us say about 2 degrees tail setting angle, right? So let's have a minus 2 degrees tail setting angle and repeat the calculation. The same question will have minus 2 degrees tail setting angle and repeat the calculation. Okay. So then we'll see what will be the corresponding trim angle of attack. Is it helping? Is the tail helping us or not? Okay. So I of t is not going to affect the stability of the aircraft, right? Isn't it? Cm alpha is not getting affected because of I of t. If you look at the equation, Cm alpha is not getting affected because of I of t. So what I of t is going to help is Cm naught. If you look at this equation, we have I of t here, right? So part D of this question is find Cm naught, or say find the trim angle of attack of the UAV with a tail setting angle of the above UAV, again the same UAV with the tail setting angle of minus 2 degrees. Okay. Let's solve this question again. So we know what is this Cm naught. Now we have the contribution from tail, right? I of t is positive, there is a definite value, it's not 0. So there is a contribution from here. Okay. We can't neglect this term, just like what we did earlier. So the value of Cm naught with I of t contribution is equals to, so these parameters are not going to change, right? Cmac will be same as, and Cl naught will be times the xcg minus xac is also same. So what I have this as 0.005, right? So I'm not again repeating that here. Minus eta is 0.95. And what is the tail volume ratio? So this is not affected because of I of t, right? Isn't it? Sorry. St by S multiplied by LT bar. 0.323 multiplied by CL alpha of tail, which is 4.85. What is CL alpha of tail? I'll just refer it again. 4.58. So multiplied by I of t here. Epsilon naught is 0 from the given data. So I of t is minus 2 degrees. So I need to convert it into radian because this CL alpha is in radians here, right? 2 degrees multiplied by pi by 180. So converting it to radians. So to radians. Okay. Degrees multiplied by pi by 180. I'll convert it to radians. So what I have is 0.05 plus a positive contribution, right? Minus of minus. I have a positive contribution because of negative tail setting angle, which is 0.0475. So with this, what I achieved is 0.0525. So Cm naught now is a far better value, at least in the order of 10, right? compared to earlier case. So what I have is 0.0525. Now again, by substituting that Cm naught and alpha, like Cm alpha is going to remain same. So alpha trim I can figure out by minus Cm naught upon Cm alpha by substituting that here. So alpha trim is equals to minus Cm naught upon Cm alpha. So minus of 0.0525 upon minus 0.5 approximately, I should say 0.48. So this is like minus 0.5, it is like 0.1 0.134 radians, sorry, 0.109 or 0.11, which is approximately 5.7 degrees or 5.6 degrees. Yeah. So alpha trim is approximately 6.3 degrees approximately. 6.3 degrees. See, now you may be flying close to that maybe aerodynamic efficiency, right? Higher aerodynamic efficiency here. So you are now able to trim the aircraft automatically without any elevator deflection at 6.3 degrees. So that's the significance of I of t. No, that is how it can contribute towards static stability and helps you to trim at positive angles of attack that we have discussed from the starting of the stability course, right? Okay, thank you.